My name is Ken Noda. In this presentation, I'm going to talk about design method for the joint arrangement of shells with CLT panels. The title is Topology Optimization of Multidirectional Link Elements for CLT Shells. CLT is a timber panel component manufactured from dimensional lumber while cross-laminating. The cross-lamination gives the panel a bidirectional stiffness. This picture shows the CLT cylindrical shell, which I structured or designed. As a panel component, CLT needs be appropriately connected to construct the shell structures, and such a shell occurs in plane and out of plane stresses. Therefore, the joint, called a link element, should have stiffness in axial, in-plane shear, out-of-plane shear, and bending. Regarding to a link element, in-plane and out-plane shear stiffness are given by screws with steel plate and diagonal screws. The bending stiffness is given by the tension of the lag screw bolt and the compression of the CLT. And the connector also transfers the axial forces. Each connector is arranged as shown in this figure. These are aggregated into one link element with 4 springs for analysis. In order to clear the CLT shell properties, this model was analyzed under dead loading. It consists of 5 pieces, each of which is joined by 6 link elements, for a total of 24 link elements. The contents of the CLT and the link element are shown here. And here is compared the stress state of a discrete shell with a continuous shell. For in-plane stresses, the discrete shell shows a large in-plane moment in the bottom panels, while for out-of-plane, a bending moment concentrated on the link element at the center apex. So in the CLT shell design, it should be fully considered that the force flow is different from continuous shells. So we focused on the link element and proposed a method to find the reasonable arrangement. In the optimization, the weighting parameter rho to multiply each spring stiffness were used as design variable. The parameter variation means to increase or decrease the screw numbers in practice. Since compression is transmitted by CLT contact rather than LSB, only tension is considered for axial stiffening. And since the tension and the bending stiffness are transmitted by the same LSB, the same parameter were used. As an optimization problem, the elastic strain energy is minimized by SQP, and the total stiffness of all link elements was used as a constraint. Firstly, the link element position is fixed at a pitch of 1 meter, and the stiffness parameter ranges from 0 to 2. It is the parameter distributions for each stiffness. The left shows the tension and bending stiffness, middle is in plane shear, the right is out of plane shear. The colors indicates the parameter magnitude, white for 0, and red for 1, and black for 2. Next, we try to find the optimal link element position. As the initial condition, the link element arranged at a pitch of 250 mm, and the parameter is optimized is range of 0 to 1. And then it was applied to find the optimal link element stiffness, and position simultaneously. Regarding to the weighting parameter distributions, the bending stiffness is weighted around the central apex. This enhances the stiffness to reduce the cylindrical features that contract inward under dead load. For the in-plane shear, it is weighted at the bottom. This gives the bottom and the second panel a stacked beam effect. Further, for the variable position problem, the weighting parameter is concentrated near the panel end. The out-of-plane shear is weighted at the bottom center and the cylinder end. This shows in 8P shell. A model with 42 link element is used as a reference, against which the link element stiffness or position is optimized. Compared to the 5P shell, the strain energy reduction is significant, indicating the method effectiveness of this. In conclusion, focusing on the link element stiffness of CLT shells, a method for optimizing the arrangement as proposed. Under the condition that the total stiffness is constant, the optimal stiffness distribution is revealed. In the future, the improvement of the method and application to structure design is attempted. With this, I will end my presentation. Thank you very much.